Hello, welcome back. We're going to go over collections in this video along with structs. Uh, so without ado, let's get into arrays. As you can see here, I've declared an array here. Arrays live on the stack and they can only have a single data type associated with them. That's the one thing that makes them different than tuples. As we declared before, tuples can have multiple types, so can be 5 and 3 like that. Can mix up our values. The arrays live on the stack and the size of an array is fixed. If we wanted to be real specific about what this array is, we can annotate it. We want it to be signed 32 bits and there's 3 of them. Sorry, semicolon. And we can use this same semicolon syntax to specify the array itself. If we just wanted to initialize all these values to 0, we could, instead of 3 values of 0, like so, we can do 0, repeat this 3 times, and that's the same thing. Pretty standard as well. You can access elements of an array by using a square bracket notation. If we try to access outside of our bounds of our array, let's say I want to get the 4th element, our program will crash. So sad. Now let's say we want to do something with our array here. Let's instead of making it 0, let's make it I'll make it back to 1, 2, 3. Let's say we want to write a double function. And this function is going to take in an array, and then it's going to return nothing actually, but it's going to double all of our elements in the array. So if you'd like, take a minute, pause the video, think of how you would write this double function that would double all the values in my array. Alright, I'll first start by declaring our double function here, and it's going to take in an array that is a mutable reference to an array of type i32, not going to return anything, and we're going to loop through every element in this array. To do so, we'll do for element in array, and at this point we're dealing with references, not the actual values themselves. So we can do something, we have a couple options here. We can do dereference, the value of L is equal to the dereference value of L times 2. That's completely valid. We can also do something like the value of L times equals 2. And I'll go ahead and call our double function up here. And we'll pass in a mutable reference to my array. Return, or should I say make this a statement. And then let's also debug my array afterwards. As you can see, 2, 4, 6. Next up, structs. We talked about them a little bit before. Structs are a way of organizing data and can be roughly thought of as classes in other languages. I say roughly. We could make a car struct that holds a make and a model with type string. I'll make these heap strings, not string slices. It would make sense in this case, wouldn't it, to have these to be a string slice type, the primitive type of string, str, instead of a heap string that we can modify, because we don't necessarily want to be able to update the string values of make and model. And the reason why we're sticking with string, the heap type, the instance, instead of str is because we haven't gone over lifetime specifiers yet. We can't pass in a hard-coded value of str here. We have to be using references, and that means we need to understand lifetimes, which we haven't gotten to yet. So we're just going to stick with the heap version of a string for now. And just to make it abundantly clear why we can't use the primitive type str is because then we need to know, we don't know the size of this at compile time. We're basically defining a struct and putting aside specific chunks of memory for this car struct because we're going to be using the struct on the stack, and these will be on the stack, but we don't know how long this str type will be. That's why we need references and fixed sizes of these variables within the car struct. Next, we're going to create a new car structure by doing something like let my car equal car. We'll pass in a make of Toyota. And then there's a couple ways we can turn string slices into string heap instances. We can do a dot to string on a string slice. We could also do string from Toyota. I think it's a little bit cleaner to write it as toString though. And then model. There we go. We have now created a new car instance that is this car struct with this make and model. We can then access the make or model of our car by using the dot notation. So I could do my debug my car dot make. But what I should do in this case is, and I should probably do it with both of these, is because I'm passing in ownership again to this debug statement. So I'll go ahead and just make them references. And I can debug a reference to my car.model and then run our program. We can also, like classes on other programming languages, write functions inside of our structs. Let's say instead of debugging, we want to print out the make and model of our car. Instead of mixing up our data, we're actually not allowed to do something like print my car function. You can't do that in structs. You got to use an IMPL block, and this helps keep our data from our struct separate from the logic that we implement in it. Literally implement IMPL car. I'll do function describe car, and that again keeps our program logic separate from our data. And I'll pass in, to make it a method, a reference to self. And we make it a reference because, again, we don't want to pass ownership of self to this method. One of the few cases why we would actually want to pass in ownership of self is if this is like destroying the car, because this will consume self, and then unless it returns self again, which it really shouldn't, it's going to consume it. No one's going to own self anymore, and it will become invalid. But anywho, we'll go ahead and print out our make and model, like so. And again, I'll make this a reference. And we should print out a reference to self.make and a reference to self.model. Because again, if we're passing in these makes and models without referencing them, then our print statement, our print macro is going to take ownership of make and model, which we don't want in this case. We just want to print out the references to make and model. We could also go ahead and define a constructor in our IMPL block, or our implementation block. By default, we use new to describe a constructor, and this is going to return an instance of self. And the Rust compiler is smart enough to know that, we're talking about a car. Self should mean a car. So I'll give it, we should take ownership of a make, which is a string, and a model, which is a string. And we'll return a new instance of self. This is like calling car. It's the same thing as doing car, make, model, but we're going to use self in this case because this is a constructor. And we're going to take in make, model, model, and that's our constructor there. So now instead of having to instantiate our car like so, because this is a static function on car, we call it with a double colon operator. Car new, and our make will be, again, Toyota .to string, and Tacoma, if I can type, .to string. Same thing that we just wrote before. And instead of debugging our make and our model, we can now call my car .describe car. And as you might notice, we're using dot syntax on methods that are described in the car struct, and then double colon for what would be akin to static functions. We didn't describe self as our first parameter to this new function, which makes it a static function on the car type. Go ahead and save and do cargo run. As you can see, we get Toyota Tacoma once again. We're also able to define structs like a tuple. I can make a point struct if we want. This is just for example. I'll go gloss over real quick. Go do struct point, and it can hold 3 integer values like x, y, and z. It's kind of like a variant in an enumerable, except it's not tied with the enumerable, right? Okay, 2 new types down, 2 to go. The next 2 aren't primitive types, but they are implemented as structs in our standard library, much like strings. In case this is starting to make sense now, a string is implemented as a struct. So when we do, and I'm talking about the heap version of string, so I could do let my string equal string new. Kind of the same syntax, right? We're constructing a string. But anywho, we're going to move on to vectors now. Vectors, unlike arrays, are allocated on the heap and allow us to add and remove elements from the collection. It's kind of akin to how string slice is like the baby version of a string on the heap, or string instance. It's kind of like the same as an array type of like i32s is the same to a vec type of i32. Kind of makes sense, right? Because the string slice lives on the stack, string instance lives on the heap, arrays live on the stack, vectors on the heap. You can add and remove elements to the string instance, much like how you can add and remove elements to the vector type. We can create a new vector by doing vec new, so I'll do let my vectory, I kind of like vectory, equals vec new. We can then push elements to the end of the vector, which is also a collection, with vec push. We need to import the vector type since that's not included in the prelude, so we'll do so from the standard library by using standard library. It'd be vec, and we'll go ahead and check everything, and we'll push a 5 to our vector. And of course, it's called my vectory, not vec. And of course, we need to make it a mutable type since we're adjusting the value of it. And make that an actual macro. As you can see, holds an element of 5. Rust also provides us with this handy dandy vec macro. It's a shorthand way of saying make a vector and add these provided elements to it. So instead of making a new vector and pushing to it, we can do something like vec 5, and that just does the same thing. We could technically index vectors like arrays using square brackets, and since we're not mutating it anymore, I'll just remove the mute keyword. Do 5, 4, 3. We could do something like my vectory 0, but it's going to panic the same way as with an array. So we could also do my vectory dot get 0, and that's going to return a option type. So it'll be either some or none, much like we've used before. And we can annotate this if we so choose by doing vec I32. Finally, let's take a look at hash maps. The concept should be pretty familiar. It's just a way to map a key to a value. I'll make a new one by first importing it, since it's not included in the prelude, from collections, hash map. I'll now create a new hash map, and we can annotate it if we so choose, or let the compiler infer. I'm just going to let it infer this time. And but again, they still need to be all of the same elements for both the key and the value. So I'll do this hash map new, my hash map dot insert, and I'll do something like blue, if I can type, and like 42. And of course I gotta make it mutable. We can iterate over hash maps like for key val in my hash map, something like that. Or to get a value, we can do my hash map dot get blue dot to string. Same idea. And that's it for this video. We're back to the exercises, so I've included a couple in the exercises repo for you to try on your own time. In the next video, we're going to look into like module resolution stuff. So as in, what does it mean when we use the use keyword, and also how to structure your project with multiple files and organizing your code